Conversion to esters. You have this glucose, the alpha ionomer, and you are treating with pyridine and acetic anhydride. So you will get this huge structure, pentacetate derivative. Treating a monosaccharide with excess acetic anhydride and a weak base such as pyridine or sodium acetate converts all of the hydroxyl groups including the anomeric hydroxyl to ester groups. If the reaction is carried out at a low temperature, in case a 0 degree centigrade temperature, the reaction occurs stereospecifically. The alpha ionomer gives the alpha acetate and the beta ionomer gives the beta acetate. Acetate esters are common protecting groups for carbohydrate hydroxyls. This is your glucopyranose. If you give excess acetic anhydride in the pyridine solvent, then you will get penta-O-acetyl D-glucopyranose. All these OH groups will be converted into OAC group. Now see this mechanism. First you are adding this CH3OH and H2SO4, that means you are forming glucoside. Then you are adding excess acetic anhydride and pyridine. So here you will get 4 OAC group. Because at first this one is being protected by forming glucoside, so 4 OH groups are now free. So that 4 OH groups will form OAC. Conversion to cyclic acetals. If you have a diol like this, and if you take acetone, this will form cyclic acetal in case of acidic solution. And the only requirement is that this diol should have to be cis. That means from the same position. If this is in the up position, this OH should also be in the up. And here the single bond can rotate, so there is no problem. If the 1,2-diol is attached to a ring, as in a monosaccharide, formation of the cyclic acetals occurs only when the vicinal hydroxyl groups are cis to each other. For example, alpha-D-galactopyranose reacts with acetone in the following way. Now see, in case of alpha-D-galactopyranose, as this is the alpha, so this is in the down position, because here the equatorial position is the up, and similarly this equatorial position is the down position, because in case of this carbon the axial position is the up. So these two are in the down positions, so these two hydroxyl groups are in cis position. So these two can form this cyclic acetal. You can see. Again see this 2 OH. Here the axial one is like this. This is the axial down. So this OH is in the equatorial up. So this one is the up position. And this one is the axial up. So this hydroxyl group is also in the up position. So these two vicinal OH groups are cis to each other. That's why these two also can form cyclic acetal. Isopropyridine derivatives of the monosaccharides. Sugars condense with anhydrous acetone in the presence of hydrogen chloride, sulfuric acid at room temperature to form mono and diisopropyridine derivatives. These are stable towards alkalis but are readily hydrolyzed by acids. In the diisopropyridine derivatives, one isopropyridine group is generally removed by hydrolysis more readily than the other, and thus by controlled hydrolysis it is possible to isolate the monoisopropyridine derivative. For example, diisopropyridine glucose may be hydolysed by acetic acid to the mono derivative. This is your alpha D glucose, and you are for giving acetone in the HCl medium. So you will get this. It was your 6-member ring, but in case of glucose, this will form 5-member ring to form the diisopropyl derivative. So from this, if you add acetic acid, this one will be hydrolyzed faster than this one. So here you are adding acetic acid, so this group will be removed and you will get this diol, and this is the monosubstituted isopropyl derivative. Here see that one isopropyl group is generally removed by hydrolysis more readily than the other. Similarly, if you add dimethyl sulfate in basic solution in this diisopropyl derivative, then this free OH group will be converted into OCH3, the 3 number of OH, the OH in the third carbon. Now if you add HCl, then you will get this. These groups will be omitted. And now after that, if you add dimethyl sulfate and HCl, all these rest of the OHs will converted into OCH3. Except this anomeric OH. Actually it is in the Fischer projection. These all groups are in the Fischer projection. If you want to see the Haworth position or the chair form, start with the chair form of alpha D glucose and you can similarly see the Haworth projection. It is much more easier to understand in Haworth projection. You had this 6-member ring, you are adding acetone and HCl, you will get a 5-member ring for glucose, because this 5-member ring give you this diol, that means this cis diol. Now if you add acetic acid, then at first this group will be omitted and you will get monosubstituted isopropyl group. And then if you add dimethyl sulfate and HCl, this free OH groups will be converted into OCH3 group. And here you are adding dimethyl sulfate and base, so this OH, the third OH, will converted into OCH3. And now if you add HCl, if you give acidic medium, then this will be opened, this also will open, and you will get this, which will readily give you the 6-member ring. Acetone usually condenses with cis hydroxyl groups on adjacent carbon atoms, the condensation occurring in such a way as to favor the formation of the diisopropyl derivative. For this to occur, the ring often changes size. In case of glucose, mannose, gulose, idose, 5-membered furanose ring forms, which I was telling that in case of glucose, you are starting with 6-member ring, but after adding acetone to form a diisopropyl derivative, the ring size will be changed and you will get a 5-member ring. In case of glucose, you will get this kind of structure. In galactose, diisopropyl derivative adopts pyranose structure. In case of galactose, there is no change in the ring size. This is the Fischer projection, that this 2OH and this 2OH will form the derivative. I have shown here the Haworth projection. I didn't have much more time to draw it. So that's why I have just done it by my own hand. I couldn't use the molecular formulas, molecular desk tools. So now see that this is your anomeric OH and this OH is in the back. So this OH can be in the up, can be in the back. So if you are taking the alpha anomer, that will be in the back. So now both of these OH are in back. So you will, these two will condense. And now see, this OH and this OH both are in the front. Even this CH2OH is also in the front, but these two will give the derivative. Fructose can form two diisopropylene derivatives which both contain the pyranose ring. So in case of fructose, there are two possibilities. In case of fructose, these were the C double bond O, right? So now if this OH attacks from the left, this OH will be on the right, and now this OH and this OH will make the derivative, and this is the similar for both case. This portion is the same. This two OH group will form the derivative. But if the ring closes from the right hand side, then this OH will be on the left. Now if this OH is on the left, you had one OH here on the left, that means this OH is on the left. So now these two OH will be cis. That's why these two can condense to give the derivative. So in case of fructose, there are two possibilities. Not only does acetone condense with sugars, but so do other oxo compounds such as formaldehyde, acetaldehyde, and benzaldehyde. Benzaldehyde condenses with two cis hydroxyl groups on alternate carbon atoms of D-glucose. You are taking D-glucose and adding benzaldehyde. So in case of other acetones or any other derivatives, two adjacent carbon atoms were participating, two hydroxyl groups of adjacent carbon atom. But in case of benzaldehyde, the case is little bit different. Here you will get a 1,3 derivative. That means 1, 2 will not participate, and 3, 1 and 3 will participate in making the derivative. Just look at with methyl glucopyranoside in chair form. You can see that this OH is in the carbon 4 and this one is your carbon 5. This one is the carbon 5. This CH2 is the carbon 6. So 4 number of OH and 6 OH. The OH attached with the carbon 4 and carbon 6, they will participate in making the derivative. So this type of structure they will form. So you will get methyl 4,6-O benzylidene alpha D glucopyranoside. Now this is an exercise how to do the following transformation. Try it yourself. If you can't do, then I am just giving the answer for this problem. At first start with the beta D glucopyranose, then convert it in the 5-member ring. If you add acetone, this 6-member ring will opens up and will form a 5-member ring. Then these OH groups, these two OH and these two OH, which are cis to each other, they will form the propylene isopropylene derivative here and here. Now just add ruthenium tetroxide and you can just oxidize this OH. You are just oxidizing it and making it a ketone. So if you add HCl now, if you add dilute acid, so this isopropylene derivatives will be opened up and you will get back the hydroxyl groups. So this is in chair form and this is in open ring structure. So just remember this one, the ruthenium tetroxide, which can oxidize this CHOH to C double bond O. Now selective methylation of C3 hydroxyl group of D-glucose. So you have selectively methylated the C3 hydroxyl group. So for this, at first just add acetone in this glucopyranose ring. So this will form a 5-member ring and a di-isopropylene derivative here and here. Then just add Me2SO4 and NaOH, or you can also add acetic acid and methyl iodide. So this, if you add Me2SO4 and NaOH, this NaOH will take up this proton, which is the only acidic proton here, and then this O- will attack this methyl group. So you will get this OMe. Now you just give acidic medium. If you keep it in acidic medium, hydrolysis will occur and then you will get the OHs free again. So now this was your 5-member ring and this will become a 6-member ring, which will remain in equilibrium. Phenyl glucopyranoside synthesis. So you are taking D-glucose and you are adding acetic anhydride and zinc chloride at 0 degree centigrade. Then all these OH will be converted into AC, all these 5 OH, including the anomeric carbons OH. Now if you add acetic acid and HBr, if you add this HBr, this bromine minus will just attach here. Actually this bromine will take the axial position due to the anomeric effect. And then if you add PHOH in silver carbonate, that means you are taking phenol. So this phenol will just make an SN2 reaction. So this phenol will attack from here. Okay, this phenol will attack from here and this bromine will leave. So you will get this OPH at the left hand side. And if you just treat it with ammonia and ethanol, then you will get phenyl beta D glucopyranoside. That means all OAC groups, all these groups will be converted into OH. Whoo, ha ha ha, uri baba, uri baba. Now come to anhydrous sugar. The anhydrous sugar is obtained when the axial CH2OH group reacts with C1, that means the anomeric carbon of beta D altropyranose to form a cyclic acetal. Okay, so what is happening here? You are forming a cyclic acetal. But the case is that you are taking beta D altropyranose, just make the ring flip, then this CH2OH will go to the axial position and this OH will also go to the axial position. So now if you just, okay, you are giving some acid, this oxygen will give its electron here and this OH will leave. that means OH2 plus. So the deprotonation will occur, and now this OH will give its electron pair here. So ultimately this structure will be formed, and after the deprotonation you will get this anhydrous sugar, 1,6-anhydro-D alpropyranose. This is called anhydrous sugar, where this CH2OH is forming bond with this anomeric OH. Actually this is the internal conversion, where one molecule of water is just ejecting from this molecule. That's why this is called anhydrous sugar. With beta-D-glucopyranose, however, it requires that all 4 OH groups become axial, and therefore the reaction must proceed through a very unstable conformation. For this reason, D-glucose requires much more drastic reaction conditions compared to D-altrose. So in case of D-glucopyranose, beta-D-glucopyranose, the anhydrous sugar formation is also possible, but that requires some drastic condition, because you have to make the ring flip, which is very much unstable, because all these OH groups are in the axial positions. All these 4 OH groups are in the axial positions. That's why this is very much unstable conformation. But still, if you supply that much energy, this can form anhydrous sugar. So at first this OH will leave, and this will form a double bond. Then this OH will attack here, and you will get this structure.